Hello, everyone, and welcome to the live session for today, January 30th, 2026. My name is Matthew. I am one of the instructors for our online classes, and I do behind the scenes stuff here with Teach Astronomy and Astronomy State of the Art. Welcome to our live session. For those of you who are new with us, welcome. We are excited to spend this Friday morning with you. Make sure you hit the like button and join our channel so that you can find out, click the bell icon so that you hear about upcoming live sessions. We host these about every 2 weeks. For those of you who are here from our courses, welcome. For those of you who are here from another source and didn't know that we have online classes, you can check out the link to our online classes on Coursera that I posted in the chat. The way this works is that you post your questions in the chat. I will grab the questions from there. I try to go in order generally that the questions are asked, but I do jump around a bit to try and give a variety of people a chance to have their questions covered and to cover a variety of topics. We will keep these at a beginner level. So if you have advanced questions about details of mathematics and quantum mechanics, this is probably not the right venue for that. So I will focus on those beginner level questions that everybody can enjoy and appreciate and understand. Ask your questions only once. I see everything. And if I skip over your question, I will either get back to it when we've had a chance to give everybody, get everybody's question in there, or it might have been too advanced and we'll come back to it in another session. Chris, do you have a topic for us today that you'd like to kind of prompt us with to get things started?
Okay, hello everyone. Yes, we'll get started straight away since we're a bit late. A topic I wanted to talk about today is the Hubble tension. I think it may have come up previously, but there's been progress or more research on that. So the Hubble tension is something you may have read about in online or in newspaper articles even, as opposed to just pure astronomy sources, because it seems to be a big deal in cosmology. It relates to a disconnect or a disagreement between two different ways of measuring the expansion rate of the universe. The measurement of the expansion rate of the universe is characterized by the Hubble constant. So this Hubble constant was first derived by Edwin Hubble in the 1930s based on the measurements of nearby galaxies, and he showed that the universe was expanding. So it's a foundational aspect of modern cosmology to say how fast the universe is expanding. And the number is usually given in units of kilometers per second per megaparsec, which means if the Hubble constant is 70 kilometers per second per megaparsec, every megaparsec away from the Milky Way, that's about 3.25 million light years, the velocity of a galaxy moving away from us is 70 kilometers per second. Go twice as far away, and the velocity is twice as high, and so on. The Hubble tension relates to a growing conflict between two different ways of measuring the expansion rate. One is based on local universe physics, which basically involves Cepheid variables as standard candles or standard measuring tools for measuring the distances to galaxies out to about 50 or 100 million light years, which is still the local universe. The project to do this has been going for decades, actually. It was improved by the Hubble Space Telescope and has been refined over the years. So it's a very mature method, and it returns numbers that are in the low 70s, 71 to 72 kilometers per second per megaparsec. And that's the expansion rate. And the error bars are gradually coming down as people do more work. However, there's a second way, and that is to use a model of the expanding universe and tether it at the microwave background radiation, which was emitted when the universe was 400,000 years old. So this is an early universe measure of the expansion rate. But the two have to agree because a self-consistent model relates the expansion then to the expansion now. Early universe measurements using the microwave background give significantly lower Hubble constants, 66 or 67 kilometers per second per megaparsec. Now that difference of 4 or 5 may not seem like much. I mean, it's about 6 or 7% difference between the two measurements, but the precision of the measurements is increased to the point where it is a big disagreement. So basically the measurements haven't changed, but the precision or the error bars attached to them have shrunk, and that makes the discrepancy larger. Based on the results from the dark energy survey from Kip Peak and recent large surveys, the discrepancy, which used to be at a level of 4 or 5 sigma, has grown to over 6 sigma. Now, in scientific terms, sigma is a relation of the dispersion of a measurement with random errors. You expect 66% or 2/3 of measurements to be within plus or minus 1 sigma of the mean measurement. So when something is 6 sigma away, it's way down in the tail of that distribution of randomly distributed errors. And it means the odds of that agreement happening, that disagreement happening, if you're measuring the same thing, is a tiny number. It's like 1 in a billion. At that point, you have to take it seriously. So the Hubble tension has been present for a while, this issue. It's getting worse. And people are now arguing whether one of the two measurements is somehow fundamentally wrong, or maybe more excitingly, whether new physics is required in the expanding universe model to make these two measurements agree. So you'll have to just stay tuned because this is an evolving research subject and the answer isn't yet clear.
Excellent. Thank you for that primer, Chris. If anybody has questions about this or related to the Hubble tension or any of the topics that Chris brought up, please post those in the chat and we'll grab them from there. The first question that we have for today is from a live participant who asks, Sir, is the multiverse theory mathematically proven, or is it still just a hypothesis, or maybe is it just an idea?
It's somewhere between an idea and a hypothesis. It's absolutely not proven. It comes from the fact that there was a quantum genesis of the universe, because if you trace the Big Bang model back to very, very early times, when the four forces of nature presumably were unified in a theory we might call quantum gravity, then you have the possibility for quantum fluctuations spawning other spacetimes. And that's the essence of the multiverse idea. But it's an idea based on physics that we don't fully understand, which is the convergence of the four forces. So we don't have good enough physics to talk about the multiverse idea, even though it's a plausible hypothesis. And it certainly hasn't been tested. And some people are wondering whether it will make testable predictions. And if it doesn't, then of course it sits in limbo as a not very useful scientific idea.
The next question is from Wendy Traver, who sent an email. The question is, don't all cosmological theories that state the Big Bang wasn't the beginning, such as cyclic cosmologies, defy entropy?
Not necessarily, because they invoke other space-times, and the entropy calculation therefore has to relate to extra dimensions. So cyclic universes theories particularly are based on an extension of standard cosmology into more than the 3 dimensions of space and 1 of time. They're called brane theories in some sense because they involve 4 or 5 dimensional space-times within which our universe is a subset. And because of that deviation in the number of spatial dimensions, the calculation of entropy also has to accommodate that. And so the entropy canon, even while it would seem that the entropy is violated in the universe we occupy, that's not the full physical situation. And so in the larger situation of extra dimensions, the rules of entropy and thermodynamics could still apply.
The next question is again from one of our live participants. David Grauman asks, please explain how neutrinos with no charge and minimal mass can accelerate the shock wave from a supernova explosion.
Well, neutrinos are, it's not that they are causative in the shock wave of the supernova explosion. They're carried along with the explosion. They're produced in the high energy particle reactions that are part of a supernova. And so enormous flux of neutrinos comes out and high energy radiation. But the shock wave is created by the mechanical impulse of the radiation acting on gas, causing shock waves. Neutrinos interact so weakly with normal matter that they cannot themselves generate a shock wave.
The next question is again from one of our live participants. David Gold asks, where can the golden ratio be seen with the naked eye in the field of astronomy?
Well, the naked eye is not going to probably see it in the sky, but the golden ratio manifests in nature in a number of ways. It's mathematically related to the Fibonacci series. The golden ratio is an irrational number. that appears in classical architecture, and in human terms, it's considered aesthetically pleasing proportion. But you can find it in living creatures, in chambered nautilus, in a sunflower, in the buds in a sunflower, and in a number of other places. But I've never seen the golden ratio manifest in the sky in any particular way.
The next question is from Illyria Moon, who's on with us live. Hi, Professor Impey. I picked up your book, Shadow World, and I'm enjoying it so far. I was wondering if you're working on or planning any new writing projects.
Well, thank you for that. It got a little traction, that book. I wrote it about 10 years ago. Shadow World is a science fiction novel, or fantasy if you like. I'm writing an periodic table book for MIT Press, a book about iconic elements, not all of them, but 8 particular ones. And that's my current project. So I don't have a fiction project in play at the moment. Maybe in the summer I'll get time to do that.
The next question is from Marcos Georgiou, who asks, can you elaborate on the relationship between particle horizon, observable universe, cosmic event horizon, and physical universe?
Right. Well, the cosmic event horizon is usually applied to black holes. So the conventional framing of an event horizon is the Schwarzschild radius of a black hole, beyond which all information is trapped, so no light or matter can escape. That's a particle event horizon is related to the way the universe expands and the largest distance from which we can have had information in the 13.8 billion year old age of the universe. And that implies that the physical universe, to use that term, is larger than the observable universe, because the observable universe is limited and defined by the particle horizon, which relates to the way the expansion rate has changed over cosmic time.
The next question is from Natalia Pastor, who asks, do you know any information about the Artemis II mission? Will it have any astrobiology research objectives on the moon or in space?
So Artemis II is priming to launch the enormous space launch system with the Orion capsule at the top of it. Has been wheeled out of a gantry at Kennedy Space Center to its launch site, and it's expecting a launch sometime in an early February launch window. These 4 astronauts, are not going to go to the moon. They're going around the moon. They're orbiting the moon. The landing will have to wait for Artemis III, which will be another year and a half later. So we have 4 astronauts on board, some veterans, also some firsts, because these are astronauts leaving the Earth's gravity for the first time since Apollo. And on board, among the astronauts are to leave the Earth's gravity or go to the moon, the first woman, the first person of color, and the first non-American. So it's kind of an interesting crew of 4. They will have a series of, biological zero gravity type experiments because they're doing a 10-day journey in zero gravity. But they're not, again, landing on the moon, so they're not doing experiments on the moon. And doing experiments on a journey like this is not really any different fundamentally from doing them on the International Space Station. So it's not, a magnificent opportunity to do science, I'd have to say. It's really just about proving the technology to get to the moon. They are, however, carrying a very interesting manifest of objects, time capsule type objects that they're carrying to go around the moon. And you can go to NASA website for Artemis II and see a list of these objects. So that's an interesting aspect, including some historical things. They are carrying, for example, a swatch of the Wright brothers flyer from 1903, the first plane, from the fabric of the wing, and some other physical artifacts from the history of aviation and spaceflight. So that's kind of a nice thing to do.
The next question is from Ravi, who sent an email. I think I understand how declination relates to pointing the telescope relative to my latitude, but I'm not at all clear on right ascension. So the question goes on, but can you talk a little bit about what right ascension and declination are and how one uses them in terms of finding objects in the sky?
Right. So when we want to navigate on the Earth, we use longitude and latitude, which relate to the Earth, and its reference points are the equator and the north and south poles. Telescopes, however, have to account for the 23.5-degree tilt of the Earth as it spins. And so telescopes use an equatorial system of coordinates, which is at an angle of 23.5 degrees to sort of standard Earth coordinates. And so measuring angles in that tilted reference frame, and that's what you'll see with a modern telescope. You'll see it on an equatorial mounting, which has the main tube of the telescope tilted as it pivots across the sky. So the coordinates for a telescope are not latitude and longitude, although you can map into those coordinates. They are declination, which is the tilt of the telescope between the north celestial pole and the celestial equator, and right ascension, which just means the angle of the telescope with respect to the rising and setting sun. And it depends on local time, of course, because the Earth is moving. So these are the standard coordinate systems for astronomy, and so object catalogs in astronomy are not listed by latitude and longitude because those are Earth coordinate frames. They're listed with right ascension and declination, which are celestial reference frames.
The next question is from one of our live participants, Educate Yourself with Me. Now, the question is specific and you may not be able to answer because you may not know the ins and outs of the Indian education system, but you can talk generally. They are somebody, they want to know what are the steps I should take as an Indian aerospace engineering aspirant, like somebody who's aspiring to be an aerospace engineer, to get involved in space or the space industry. So again, you may not know the ins and outs of the Indian system, but you can talk about generally.
However, I do know the Indian educational system is very favorable towards people taking engineering paths. So it's actually easier to study engineering in Indian universities than to study pure science like astronomy. So if you're interested in aerospace engineering, you're in the sweet spot as far as the Indian economy, as far as their university system. And because India is an aspirational space power, which has done some impressive things in the last few years, has plans for the moon and Mars, has its own launch capability, then I would say you'd have plenty of opportunities for employment in the Indian space sector, because they are essentially competing with Europe and the United States.
Excellent. Thank you very much. The next question is from Arona Kundu from Bangladesh, who asks, if something falls into a black hole, is the information about that object lost forever, or is it stored in the event or on the event horizon?
And that's an interesting question, and we simply don't know the answer. In conventional black hole theory and physics, the information is lost forever because nothing can escape the event horizon. So whatever was true about the object that fell in, if the object itself contained information, that information is trapped and lost forever. Now, there is a theory of black holes called the holographic theory, which speculates that information is not completely lost, and that as objects fall towards the event horizon, and of course they will do so asymptotically, with the time and their clocks slowing down infinitely, and their radiation being redshifted to the point of zero energy, and so therefore becoming black, but that the information is not completely lost, that it is essentially frozen on the event horizon. And that would correspond to something like a hologram. That doesn't allow it a mechanism, or doesn't suggest a mechanism for how to extract that information, so you're still stuck with that fundamental problem. But it's an interesting twist on the idea of a black hole, that the information may not truly be lost.
The next question is from one of our live participants. Tom Story asks, what would happen to me if I could really find myself relatively motionless in space-time? Would all the time pass and I would die instantly?
If you were motionless in space-time, that's of course a difficult supposition because everything in the universe is in motion. So the whole concept of being motionless in space-time it takes some thinking about. As you stand on the surface of the Earth, you're spinning with the Earth, you're moving around the sun, and the sun is moving around the Milky Way galaxy, and the Milky Way galaxy is moving with respect to other galaxies. So the simple answer is that it's not possible to find a truly inertial reference frame with no motion. The closest you could come to is the inertial frame defined by the microwave background radiation, That reference frame, of course, of radiation comes from the very early universe and represents the entire universe. So in principle, if you could position yourself in space such that the intensity of the radiation and the wavelength of microwave radiation you saw in every direction was exactly equal, then you would be at rest with respect to the universe at large.
The next question is from Crom Crua, who asks, are there any plans for exploration missions towards Earth's Trojan or dwarf planets and very large asteroids in the asteroid belt?
There are no immediate plans. There have been a few, of course, outer solar system missions. The one that's actively investigating in this regime, given of the 4 objects that have formally left the solar system, which is to say they passed the orbits of Uranus and Neptune, New Horizons is the one that is still potentially investigating dwarf planets and Kuiper Belt objects. The trick is that it's a long time to get out there. These are billions of miles away, these distances, and the span is enormous. Space is enormous out there. And so finding individual objects and locating individual objects is sort of a matter of luck if all you have is one space probe. And even telescopes are not greatly helpful because the objects there are so far from the sun that they're exceedingly faint.
The next question is from one of our live participants. Kamran Pandrani asks, how does a black hole attract light even when a photon has no mass?
Well, it doesn't necessarily attract light. It's just that light will fall into a black hole, of course. Light heading towards a black hole will fall into the black hole. Now, you can say that a photon with an energy E has an equivalent mass defined by the energy divided by c squared. That's equals mc squared equivalence. And so you can think of an equivalent mass for a photon, and that would be the basis for a gravitational discussion of how photons behave relative to black holes. But a photon falling onto a black hole is, of course, not going to be absorbed or re-emitted or reflected or scattered. It'll just disappear. And that's unlike most photons in the universe, which interact with matter and degrade, and they may reflect and they may absorb, but they often re-emit, and so they don't disappear forever.
The next question is from one of our live participants. What findings by Artemis 2 would have a major impact on future space travel?
Artemis 2 is a technology test of the Space Launch System and the Orion capsule. So it's not going to have any major results. It's not going to have any major innovations. It's essentially a proof of concept for the Artemis mission, which is run very far behind schedule and over budget. So people have been patiently and impatiently sometimes waiting for Artemis 2 for quite a while. Artemis 3 is really going to be the high degree of difficulty mission, which will follow in late 2027, maybe early 28, because then you'll land on the moon and you'll be doing moon operations, and you'll have to demonstrate the landing, the takeoff again. Artemis 2 has a gentler lift or a more modest mission because all it's doing is orbiting the moon a few times and then coming back to the Earth in a cislunar orbit. So it's not technically as challenging as Artemis 3 will be.
The next question is from Christina, who sent an email. And the question for Chris is, if there weren't any neutron star mergers near a molecular cloud where stars form, would exoplanets around those stars lack uranium and thorium for internal heating and cool off quickly? Can we observe any systems like that?
It's an interesting question. It's relating to the fact that neutron star collisions have given the universe most of its heavy elements. And so then the question is, if you're in a regime where those heavy elements have not been created and distributed into the interstellar medium, would planets nearby be deficient in those elements? And the answer is possibly, but maybe not, because neutron star collisions are rare. They eject the heavy elements that are created at enormous speeds over large distances. And then differential rotation and turbulent motions in the Milky Way galaxy mix that gas in with other star-forming regions and other gas clouds. So over long periods of time, what that means tens or hundreds of millions of years, the heavy elements produced by merging neutron stars do get widely distributed and more or less smoothly distributed. So there might be some really good proximate effects of a system that forms right next to a neutron star collision being enriched in certain heavy elements, but generally we wouldn't expect to see large abundance variations.
The next question is from Anjali, who's on with us live. What will or would happen if a black hole and a white hole collided with each other?
It's an interesting speculation. It's pure speculation. Black holes exist. We have evidence of them. They've been part of the landscape of astronomy for a century. White holes may not exist. They're speculative. They're possible consequence of general relativity, but none has yet been observed. So the question about a collision between them is equally speculative. Now, a black hole is a sink of matter, and a white hole could be a source of matter and radiation. So when you combine a source and a sink, it's not entirely clear what happens. And to be honest, I haven't read a good theoretical paper that speculates as to what the outcome of such a merger would be. And I have a feeling it's because white holes are so speculative that theorists don't want to do an extensive set of calculations about something that's such speculation.
So can you talk a little bit more about wormholes? Um, Kamran Padrani and several other people have asked about wormholes. You said that they're speculative, white holes are speculative. Can you talk a little bit about where the idea of a wormhole comes from, and how would one detect something like that if they
Mhm.
existed?
So while wormholes are speculative, they are rooted in the good theory of gravity we have, general relativity, where mass and energy bend space and time. So the interesting feature of this subject of wormholes as a topic is that the universe we live in is actually quite mundane. It's kind of a vanilla universe. There's not a large amount of space-time curvature. On large scales, there is, caused by gravitational lensing of dark matter and visible matter, but it's quite subtle. And then on very small scales near a black hole, of course, extreme space-time bending with the event horizon of a black hole. But generally, space-time is smooth. Wormholes are relating to the fact that theoretically, in hypothetical universes governed by general relativity, space-time could be much more complicated than the universe we live in. It could involve high-density situations where the space-time is extremely curved, where different regions of space interconnect with each other, and that's what a wormhole is, and possibly can be done between disparate regions of space by following a wormhole than a smooth trajectory through space. So you can hypothesize complex, interesting, wormhole-ridden geometries of space-time, and it's all legitimate because you can use general relativity to do so. But the universe we live in does not look like that. The universe we live in does not look like a wormhole-ridden universe, or one even where wormholes might exist at all. That's disappointing, but just the way it is.
Excellent. Thank you very much. The next question is from um, Arona, who asked a question earlier. As the sun ages and expands, what is the most realistic timeline for when Earth will no longer be able to support life?
That's been subject of some speculation and simulations. It's a steady thing, of course, as the sun consumes its nuclear fuel, as the hydrogen turns to helium by fusion. The sun reconfigures to its most compact minimum energy configuration. And so that does also mean that the sun burns at a different temperature, and it'll fuse at a hotter temperature as time goes by and its fuel is steadily depleted. It's a very slow and gradual thing, though. Some people have speculated, based on fusion models for the sun's core, that in about 500 million years, the sun will have gradually heated up to the point where at the Earth's surface, we reach the boiling point of water. And at that point, the biosphere is definitely threatened. So we don't have to wait, or it's not going to take as long as the time for the sun to exhaust its entire nuclear fuel, which is about 4.5 billion years. It's quite a lot sooner than that it'll already be running hot enough, the sun, for life on Earth to be extremely challenged.
The next question is from an email, And the question is, how would you describe an infinite universe or infinity in cosmological terms? What does that mean in terms of real cosmology?
Well, it is a tricky idea because, an infinite universe is problematic and conceptually and philosophically. And this has been known since Newton's time. So Newton was living in a time when there was no reasonable bound to the universe, and he thought the universe was infinite. And he hypothesized and explained the theory of gravity as an inverse square law in this universe. And immediately there's a problem because if the universe is infinite and therefore infinitely filled with stars and galaxies, then the total amount of gravity is infinite too. And what does that mean? If by contrast the universe is finite and has an edge, Newton knew that gravity in the interior would pull the exterior material in, and that would continue and accelerate, and such a universe would collapse. So to Newton, a finite universe made no sense because it would collapse and then at some point not exist, whereas an infinite universe could potentially be stable with the problem of infinite gravity. So at the moment, we don't have any reason to suppose that the universe isn't infinite. I'm using a double negative there. In other words, there's no evidence of a boundary except the boundary imposed by the finite age of the universe and light's travel time, light speed travel. So it is possible the universe is infinite, but our region that we can study is a subset of that potentially infinite universe.
The next question is from an email. Christina asks, if a big crunch for our universe is a possibility, could the universe be fluctuating between existence and non-existence every 30 billion years? And is this kind of 33 billion year life cycle model more consistent with the laws of conservation of energy than a big freeze or a big rip model?
So the cyclic universe model has had its phases when it's popular and then out of favor. It first came up in the 1950s and 60s as people were speculating about the Big Bang itself, and they realized there could be a expanding universe which would eventually recollapse, and perhaps that would repeat that cycle. Now, Stephen Hawking and others in the 70s and 80s decided a cyclic universe was not plausible because entropy increases through the cycle, and that means infinite increase of entropy. And since if the entropy cycles and the universe cycles are infinite, that would create infinite entropy at some point. So that's a logical, physical contradiction. So Hawking and others thought a cyclic universe was not plausible. Now we have a different constraint, which is that everything we know about the universe suggests that dark energy and dark matter and the normal matter we're made of is not sufficient to overcome the cosmic expansion. In fact, dark energy, the dominant component of the universe, is causing it to accelerate. So the odds that the universe we live in recollapse are very low, perhaps zero, because it is so clear that the universe is not only expanding, but it's expanding faster and faster, not slower and slower. So cyclic universes are now very implausible because of what we observe.
The next question is from Maja Dabrowska or Maya Dabrowska, I'm not sure how it's pronounced, who's on with us live and would like to know, can you please explain why space-time is curved near a black hole?
So the fundamentals of general relativity say that mass and energy curve space and time. Those two things are hyphenated because mass can convert into energy and vice versa, and space-time are connected in a four-dimensional continuum called space-time. And so basically, depending on the local mass and energy density, light will bend or deflect. And a black hole just corresponds to a situation where if you work out that bending or deflection angle in general relativity, the bending or deflection angle is 180 degrees. In other words, the light is turning in on itself and is trapped essentially. So just in a simple calculation in general relativity shows you that light at a black hole is fully trapped. And that's simply an extension of the curvature of space-time and how mass and energy deflect light.
The next question is from one of our live participants. If we can't see or touch dark matter, how can we be so sure it's actually there and not just a flaw in our understanding of gravity?
Well, it's a good question because the answer is it could be a flaw in our theory of gravity. It's true that dark matter, we cannot see or touch. It by supposition, it does not interact with normal matter or radiation. There are variations of dark matter theories where it's self-interacting, so it interacts with itself, and that creates some observable effects. But it doesn't interact with radiation, and that's the key of how we detect most things in the universe. So given that we still don't know what it is, dark matter theories or observations have been since the 1970s. We're up on 60 years of dark matter observations, and no evidence has come up suggesting there are places in the universe without dark matter. It seems to be everywhere. But as for whether we're wrong about it being a subatomic particle that we're searching for hard in physics labs around the world, or a problem of gravity where if you alter the gravity law, you can do away with the need for dark matter. That's clearly been done in some models. The trouble is, to alter a theory of gravity in a mild way, just to tweak gravity that we have to get rid of dark matter, you actually sacrifice some important physical principles. You sacrifice conservation and symmetry principles of gravity. You make gravity essentially an ugly theory to get rid of dark matter. The alternative is to go back to the drawing board and develop new theories of gravity, tensor or scalar theories, different kinds of theories that have a fundamentally different physical basis, and then they also make the need for dark matter to go away. And that's a very heavy lift, and no one's succeeded in doing that, and also not too many theorists are around who can work those kind of theories. So that field is probably underdeveloped.
And then to be clear, we're not talking about just overturning Newton here. We're talking about overturning um, Einsteinian ideas about gravity,
Yes, yes.
correct?
So just to elaborate and continue, if dark matter, if we're just being fooled somehow and dark matter doesn't exist the way we think it does and it's a flaw in the gravity theory, to explain dark matter away without a tweak in Newtonian gravity, we would have to go back to the drawing board, which means going beyond general relativity, because general relativity is our theory that explains the expansion of the universe. And in a theory of general relativity, dark matter and dark energy and normal matter are in the universe, and they're still working within that theory. So we would need a fundamentally different gravity theory.
Excellent. Thank you very much. The next question in our queue is from Utopian Gaia, who's on with us live and asks, where can we find extremophiles on Mars, I guess, or where would we be able to, or might we be able to find extremophiles on Mars?
Well, there are extremophiles on Earth. So extremophiles are microbial organisms that can handle physical extremes, either extremely cold or hot temperatures, or ranges of high or low pH, or extremely high or low pressure, essentially, or acid or base, any extreme of physical or chemical environment. The places where extremophiles could exist on Mars, we still need water. Life on Earth needs water. So even if life can exist in frozen situations, at some point there has to be the motility of water for cellular function to work. So the best places on Mars would be subsurface aquifers. We know that there's almost certainly water underground on Mars, so liquid right now, kept warm by pressure from the overlying rock and by mild radioactive heating from the interior. That's enough to keep water liquid. It may not be large amounts of it, just aquifers or pockets or shallow seas, perhaps, underground. That's the best place for extremophiles, because those are conditions where we know there are microbes on Earth that can persist in those. The other place is, of course, at the polar regions where we know there's a lot of water ice along with the carbon dioxide ice. And again, in some limited regions, there may be enough local heating to create water motion, and then extremophiles could live there. Those are the best places.
Thank you. The next question is from one of our live participants. How does recent progress on black hole information recovery and Hawking radiation influence our updated theories of the early universe?
Well, we haven't really solved the information paradox of black holes, which is the conundrum between the fact that information on the macroscopic level in a black hole is destroyed or lost forever, whereas particle interactions at the fundamental level preserve information forwards and backwards and across space and time. And so particle interactions at the event horizon should conserve information. And that's the gist of the information paradox. And that paradox has not been resolved. And it also is not clear how understanding better black hole physics, the physics of collapsed stars or supermassive black holes in galaxies, directly relates to the early universe, except for the fact that the universe in its very earliest stages, tiny fractions of a second, does have some of the attributes of a black hole in terms of having extremely high space densities and possible miniature event horizons and so on. But that's all speculation. We don't really have any way to convert black hole theory, macroscopic black hole theory, into early universe physics.
The next question is from Maria April. Can we, on the basis of the cosmological principle and the universality of known physical laws, assume that intelligent life can arise wherever suitable chemical and biological conditions exist?
That's a very good and carefully framed question, and it says that the predicates of cosmology, which are homogeneity and isotropy, that there's nothing special about our location in space or looking in different directions in space, give the same answer, and the fact that the laws of physics do not vary over space and time. With those as predicates, and well-supported predicates by observation, it does indeed give a good probability to the fact that the emergence of biology on the Earth was not a fluke, because we know that the physical conditions that led to the creation of elements on which life is based, hydrogen, carbon, nitrogen, oxygen, exist throughout the universe. We know that for a fact, and we've seen those elements and many molecules at large distances from the Earth. So that fact, the universality of chemistry, which flows from the universality of physics, is a good basis for believing that biology is also universal. But there's a big jump there because there's so many stages involved in going from simple inert chemicals to even the first cell. And those are steps we simply don't understand at the moment, and nor can we replicate them in the lab.
The next question is from one of our live participants. Brahms asks, could you please explain how a protostar comes to be, and how is this related to spiral arm compression in a galaxy?
So protostars are the high-density regions of gas and dust that have collapsed by gravity and are on the point of forming a stable star. So the collapse process takes several stages. There's a large diffuse nebula of gas and dust, hundreds of times maybe the size even of our solar system, and within it a collapse occurs, and stars typically form not singly but in groups. So basically a very large gas cloud, a molecular cloud, giant molecular cloud, will collapse on a large scale, and then within it on smaller scales subcollapse to form stars. And the point at which the stars go into free fall, gravitational collapse, and switch on fusion is the protostar phase. And it happens quite quickly. Protostars probably is only a phase of hundreds of thousands of years in evolution. How it relates to the rotation of the galaxy is that the spiral arms of a galaxy are not just or apparently increased concentrations of stars and gas, they also represent compression of the stars and gas. So higher densities of stars, higher density of gas increases the likelihood that the cloud will collapse to form stars. So very directly, density waves can trigger star formation in spiral arms, and that's why we see spiral arms tracing star formation in spiral galaxies, like beads on a string. The blue and white stars that have formed recently and are quite young trace out the spiral arms.
The next question is from We See the Same Moon, who's on with us live. Is the movement of the solar system within the Milky Way endless? And are there any other galaxies that have a similar system to our Milky Way in terms of shape and motion, and then our solar system within it?
There are, to answer the last part first, there are almost certainly similar geometries to the one we find ourselves in, where there are solar systems occupying positions within rotating spiral galaxies. Remember, the solar system is an incredibly small scale compared to the spiral galaxy. So the solar system doesn't really know about the spiral galaxy it occupies. And if we think about the age of the solar system, it's 4.5 billion years. And the orbital time of the solar system around the center of our galaxy is about 250,000,000 years. So if you do the math, and it's about 18 orbits of the center of our galaxy that we've done since the sun and the planets formed. So over long periods of time, the evolution of a solar system, that solar system is orbiting around the galaxy many, many, many times. And mostly the solar systems in a galaxy are immune to the large-scale motions within the galaxy. It only affects them when there are, say, compression waves due to a spiral arm passing through the solar system or near the solar system, or collisions of stars, which are basically random occurrences.
The next question is from Illyria Moon. Other than the standard periodic table elements required for life, carbon, hydrogen, nitrogen, oxygen, etc., what other elements are important for the possibility of life on exoplanets?
We think it's the same toolkit of elements. So there are the foundational or fundamental life elements, which are the basically four: hydrogen, carbon, nitrogen, and oxygen. But a living organism on the Earth depends on a number of other elements, and they are crucial to the functioning of the organism, even if they're not in that top four. Magnesium, for example, is a really important element. Potassium is a really important element. If you look at the energy production mechanism of ATP, that depends critically on potassium. So potassium, magnesium, calcium, these are essential life elements. They're found in all living creatures. And the total toolkit of elements that are essential for the functioning of most living creatures, including iron, for example, some heavy elements, is about 12 or 13. And then there are another dozen elements that are found at trace concentrations, like selenium and some high periodic table number elements, which we don't know if they're essential for life, in the sense that if they did not exist, life couldn't exist, but they have some critical role to play. So that's probably about a dozen elements that are essential. And they're distributed everywhere, so they're not unique to this Earth or this solar system or this galaxy.
The next question is from Jim Rittenberg, who's on with us live. Are there any estimates of what percent of the total universe the observable universe comprises?
No, there's really no way to estimate that. So the issue here is that the observable universe is almost certainly a fraction of the total physical universe, and we know that because the universe was early on expanding faster than light speed and now is not. And so there are regions that were far removed from our view that have not come into view. So that's a clear consequence of standard Big Bang cosmology, that the physical universe is larger than the observable universe. The wild card in knowing by what factor it is inflation. So inflation, if it occurred in the very early universe, it expanded space-time exponentially by 30 or 35 orders of magnitude. And then that space continued to expand with the Hubble expansion. So if that is true, then a physical universe could be, not infinitely larger than the observable universe, but larger by an enormous factor. And inflation theories are uncertain enough that we simply don't know how to estimate that enormous factor.
The next question is from David McKechnie, who sent an email. I'm wondering what the current thinking is amongst astronomers about the effects that Starlink satellites are having on observations worldwide.
Right. There's great concern amongst astronomers about contamination, light pollution, and especially orbital debris. Now, Starlink satellites are not debris. There's a debris issue too. Starlink satellites are doing a job of delivering wireless internet to developing countries, which is a good goal. I'm not complaining about their goal. But the consequence of having tens of thousands of Starlink satellites in low Earth orbit is that they reflect sunlight. When the sun is low on the horizon, they reflect it down to telescopes, taking data at night, and they contaminate with their streaks images of the sky, deep images. And early data suggest that the deep images of the sky being taken with the Vera Rubin Observatory, brand new survey telescope, or other large telescopes, is that 10 or 15% of their deep images are contaminated, if not completely spoiled, certainly compromised by Starlink trails. And that's just now. The number of satellites, not just from Starlink, but from other constellations launched by Google and other tech giant companies who have their own satellite businesses going could create a serious problem for astronomy. There are negotiations, especially for the Starlink satellites to reduce their reflectivity, and some work has been done in that area, which helps. But fundamentally, the growth of the number of satellites in their constellation of satellites is going to create a real headache for the future of optical astronomy.
Excellent, thank you. We have about 5 minutes remaining in our live session. So for those of you who are here with us now, make sure you hit that thumbs up. It helps us get the word out about our live sessions, and make sure you subscribe to our channel and click the notifications bell so that you hear about upcoming live sessions. The next question is from Marcos Giorgio, who asks, I read recently that scientists created the most detailed map of dark matter using the James Webb Space Telescope. Are there any implications or future directions coming out of that?
Yes, there's been a beautiful image released just last week, I think, about dark matter maps made with the James Webb Space Telescope. So this is James Webb doing surveys deep into the universe, looking for gravitational lensing, weak lensing, subtle deflections of light by matter. And since most matter is dark matter, these deflections essentially allow you to paint a dark matter map. And that's what you may have seen. You may have seen an image where the dark matter is color-coded blue, and you see diffuse blobs of dark matter. And then the background is a series of galaxies, typically on a red color scale, to show you where the visible light is. There's no immediate answer from the analysis of that survey. That's brand new data, and so it's not led to any redefinition of cosmological parameters, but it will, because the Dark Energy Survey is the biggest, most powerful survey with the best statistics of any telescope, and survey results continue to be analyzed. It's an enormous lift to reduce that kind of data. So having taken the data, it takes a good part of a year just to get the answers out.
The next question is from Arif Roni, who asks, how are the Pauli exclusion principle and the Heisenberg uncertainty principle different from each other?
So the Pauli exclusion principle just says that two subatomic particles can't share exactly the same set of quantum properties. And so what that does, in the case, say, of electrons, if you talk about the electron's energy and its spin and all its quantum properties taken together, charge, of course, the existence of the exclusion principle suggests a pressure. And so there's a pressure created by the resistance of particles from having exactly the same set of quantum states. So Pauli exclusion principle just says you can't have identical quantum states, and if in a region of space you do, it creates a pressure. Heisenberg uncertainty principle is more fundamental in a sense because it applies to all observations, all measurements, all particles. And it basically just says that you cannot simultaneously know with infinite precision pairs of quantities about those particles, such as their position and their velocity, or their energy and the time they exist for. So that's a very different principle, and it's more foundational, if you like. It's more fundamental than the Pauli principle.
The next question is from one of our live participants. Is a black hole circular or spherical in shape? And is there any way to visualize that other than the flat sheet, bent with some kind of heavy mass?
Right, so we use these two-dimensional analogs of curved rubber sheet for black hole, but actually that's not a good analogy of a black hole because a black hole pinches off space and time. So it would more be like a rubber sheet where you pinch apart hard enough and tight enough that it actually segregates itself from the sheet itself and is invisible from the sheet. But in 3 dimensions, a black hole is a 3-dimensional object. It's close to a sphere because black holes are always spinning. It'll be an oblate sphere, which is to say slightly wider at the equator caused by its spin. And general relativity allows us to calculate the shapes of black holes. And our observations of black hole shapes are too crude to confirm the actual shape, the oblate spheroid. That's never been done because we only see a projection in 2 dimensions, so we can't get a full 3-dimensional reconstruction that way.
Excellent, thank you. It's 11 o'clock. We'll take one final question in here. And that will be it for this session today. The next question is from Kamran Padrani, who asks, in the future, will there be any possibility of detecting or finding a ninth planet in our solar system?
There are definitely options because surveys are underway. So we have 8 planets and we have a few dwarf planets. Um, we have Pluto, which was demoted to a dwarf planet in 2005. We have Eris, we have Haumea, and there are a few others on the bubble that could be in the dwarf category. Current surveys are likely to increase that number from 3 or 4 to 7 or 8, and that will probably be the largest number we come up with. They're having to survey large areas of sky because the orbits of these planets could be displaced from the ecliptic, in other words, tilted. And that means you have to survey a big swath of sky, not just survey a little band around the ecliptic. And that's really why it'll take a few more years to have a full census of dwarf planets. But it'll come because there's more than a handful of medium-sized telescopes that are doing this work every night. Thank you for all those good questions. And I'm not sure when our next session is, but we'll be back with you in a couple of weeks.
Excellent. Thank you all for joining us. We enjoy spending the morning with you and your fantastic astronomy questions. We will be back in 2 weeks on Wednesday, February 11th. Same bat time, same bat channel. That's a old reference. I'm not sure if anybody else will get that. But we will see you then. Bring your questions, and we will talk to you in a couple of weeks. Remember, if you have a chance, please hit the thumbs up button to get the word out about our channel. And if you want to hear about upcoming sessions, subscribe to our YouTube channel, and then you'll get announcements about live sessions. Or you can join our Google listserv. If you scroll up to the top of the chat, there's a link there, and you can join that Google listserv. Thank you again all for joining us. We hope you have a great weekend, and we will see you again soon. Take care.